We are discussing the solution of Navier-Stokes equation for the Couette flow problem, in which case there is a fluid flow that is taking place between two infinite plates, such that one of the plates is fixed and other is moving with a certain velocity v with no external pressure being applied, and the fluid is steady, incompressible, and so on, and the conditions are given. And from the continuity equation we have determined that u is equal to u of y only, and it does not depend on any other thing, because steady motion, so it doesn't depend on t. It has been assumed that it doesn't depend on w either. So out of the x and y components, we have seen that du by dx is equal to 0, so it doesn't depend on x either. So the only other chance that is there is that it depends on y. So we have to note it, and we will be using it later on when we simplify the other components of the Navier-Stokes equation. So we start with the x component of the momentum equation or the Navier-Stokes equation only in the x direction. As we do that and we write down the equation with full component form, then we obtain the left hand side will be rho into partial derivative of u with respect to time, u into du by dx plus v into du by dy plus w into du by dz, and that is equal to minus partial derivative of pressure with respect to x. You will recall that in the equation we have pressure gradient appearing there. The x component will be this, and then there are gravitational forces, the x component of which is being denoted by g of x. So rho times g of x. And plus there are other terms coming from the stress components, and from all this equation, all these things turn out to be 0, as you have seen. And all that we will obtain from this is that, you remember, because of the continuity equation that is made use of here, and divergence of u will be 0 because of the continuity equation. So the only non-zero component from this whole equation will be du by dy2, that is the second derivative of this. Actually, in fact, this is d2u by dy2 equal to 0, this part. And when we write it equal to 0 and we divide by all any other multiplying scalar quantities, it will reduce to this part. So we have an equation from continuity equation which gives us u is equal to uy, and from the x component of the momentum equation we obtain another component, that the second derivative of u with respect to y is equal to 0. All other components are 0. And this is the elaboration of the same thing that I just mentioned in my earlier slides. As you have seen, they have given here the partial derivative with respect to time vanishes because of the steady motion condition, and dy by dy can give us only result. Now we do not show the details because they are not necessary. They are the same what we got it in the x component in the other direction. Then we try to write down for the second component in the y direction. We will obtain, when we try to write that, then the total component of x of the momentum equation in the y direction, the only thing that will be non-zero will be delta p by delta y, the partial derivative of p with respect to y, and that will be equal to 0. All other terms will vanish and they will not be contributing anything. So this implies that p is not a function of y. P is independent of Y. That's another thing that we have obtained. And similarly then, so the only in fact non-zero value for P in this case when there is no external pressure is that P will depend, however, on Z. So there is a pressure head that may exist because of the height. Otherwise, since there is no external pressure that is being applied, so with respect to the variation of X or Y, there is no contribution of P. And that can be understood because for a steady flow, the pressure variation is always computed or calculated or depends on the height. And if the height is Z, or it is the maximum value of, let us say, H, then that will be the height. If the higher H goes, the higher will be the value of the pressure, and so on. So from that, we obtain this value that if delta P by delta Z is equal to rho G. Remember, when we take this component of the momentum equation in the Z direction, it is from there that we have obtained this value, delta P by delta Z equal to minus rho G, because all other terms will vanish. And when I integrate it, this will be equal to dP by dZ equals to rho G. The partial derivative has been written as the total derivative, and that is because for the reasons that we have given above, P does not depend on either X or Y, and so we can write that, and there is no problem in the mathematical conditions. Now, when we take these equations, the results that we have obtained, then we see that one, we need to remember that U is equal to U of Y, we obtained from the continuity equation. The other thing we obtain is that du by dy2 is equal to 0. And the third equation that we have is dP by dZ is equal to 0. So combining the three, we try to look for the solution. We integrate this, and when I integrate it 2 times with respect to y, I will obtain u is equal to c1y plus c2, where c1 and c2 are some arbitrary constants. They are constants of integration. And when I integrate dP by dz equal to 0, then I will obtain this integral, and the arbitrary constant I write as C3 because I have already used C1 and C2. Now we need to obtain the value of C1, C2, C3 to be able to determine the complete solution without unknown or arbitrary constants. We apply the boundary conditions, and we begin with equation 8, in which the pressure value is given, and we need to find out the value of C3. So if we choose P is equal to P naught at Z is equal to 0, then the equation we will have the value of C3 as P is equal to P naught minus rho GZ. Or from this I can write P minus P naught is equal to minus rho GZ.